Do you ever find yourself just, scrolling, searching through endless emails, reports, social media spreadsheets, feeling completely overwhelmed by it all?
Oh, absolutely. It's
Yeah.
like this constant flood of information.
Yeah, a tsunami of facts and figures. And the big question is, how do you possibly make sense of it, let alone use it to make, smart decisions?
It's definitely a modern challenge. I mean, data is everywhere, but just having raw data, well, it often isn't actionable on its own.
Right.
It needs structure, organization, a purpose, really, to become useful.
That's exactly why today we're doing a deep dive into data organization to drive decisions. We're looking specifically at Professor Davi Morera's material on structured and unstructured data, databases, information management, all that good stuff.
Mm.
And our mission here is simple. Give you a shortcut, a way to understand how data gets structured, stored, and then used to make powerful decisions. We want to make these frankly complex ideas feel accessible, maybe even a little fascinating.
Sounds like a plan.
Okay, so let's unpack this. Before we even get into organizing, maybe we should start right at the beginning. What is data exactly? It sounds basic, but it's the foundation for everything else.
Yeah, you've hit the nail on the head. At its most fundamental, data is just raw, unprocessed facts. Figures, symbols, anything that represents some piece of information about the world.
Raw material, sort of.
Exactly. Think of it as the raw material for understanding. And it comes in loads of forms: numbers, text, images, audio, video. We generally split it into quantitative, so numerical stuff, or qualitative, which is more categorical things like names or colors, types of products, that kind of thing.
Okay, so if data is the raw ingredient, it makes sense it comes in different flavors. You wouldn't use flour and sugar the same way in baking. What are the main forms data takes?
That's a great analogy. We usually talk about three main types. First up, you've got structured data.
Okay.
This is the neat stuff. Highly organized, fits perfectly into a defined format. Think rows and columns like in a database table or just a simple Excel spreadsheet.
Like a contact list. Name, address, phone number, all in their own columns.
Precisely. That structure makes it really easy to search, sort, and analyze. And it's worth mentioning, Professor Morera's course, which we're drawing on, focuses specifically on using and analyzing this kind of structured data for business analytics.
Got it. But I look at my email inbox or Twitter or whatever. That's just a massive stream of text and images that doesn't feel very structured.
You're absolutely right. And that's the second category, unstructured data.
Ah,
This is data without that predefined format. It's the text in your emails, social media posts, videos, pictures, audio files. It's much more free form and, well, much harder to automatically process and analyze.
makes sense.
And then, sort of sitting in the middle, there's semi-structured data. It doesn't fit a strict table structure, but it has tags or markers, like little labels, that help organize things. Think of XML or JSON files that often use these tags.
Okay, so structured, unstructured, semi-structured, and businesses are just drowning in all of this, right, from all over the place.
Absolutely swimming in it. We often just call all of this business data. It's everything an organization collects: customer info, financial transactions, sales numbers, inventory, employee records, you name it.
Wow.
And yeah, it comes from really diverse sources. Purchase transactions, social media feeds, market research studies, financial reports. Understanding of these different types is crucial because it really dictates how you can store it, process it, and ultimately get some value out of it.
Which leads us right to the next big challenge. Managing it all. With all this data, structured or not, you need a smart way to store it, find it again, manage it efficiently. And that, I guess, is where databases come in.
Exactly. A database is basically just a structured collection of data, and it's usually managed by something called the Database Management System, or DBMS.
Right. The system that handles the database.
Correct. And the real groundwork for the databases we use most today was laid back in 1970 by a researcher named Edgar F. Codd.
God, okay.
He proposed what's called a relational model. It completely changed how people thought about organizing data. This led directly to RDBMS's Relational Database Management Systems.
Lots of acronyms here.
Ha, yeah, there are a few.
Uh-huh.
RDBMS. And also SQL Structured Query Language. That's the language we use to talk to these relational databases to ask them questions or update the data.
Cool, I've definitely heard of that.
Oh, yeah. SQL became dominant, really, in the 1980s. It powers huge systems like Oracle, IBM's DB2, Microsoft SQL Server, and even popular open source ones like MySQL, which tons of websites run on today.
So the core idea of a relational database, It works by linking different tables of data together, using shared fields.
That's it, exactly. Think of it
Yeah.
like, well, your library analogy was good. Different sections for fiction, nonfiction, kids' books, but one central catalog system that connects them all based on, say, author or subject.
Okay, so you can connect information across different areas efficiently.
Precisely. And the real power, especially for businesses, is how SQL lets you ask these complex questions that span different tables, different departments even, questions that used to be incredibly hard to answer.
Like what? Give me an example.
Okay, well, using SQL, you could easily pull up all the flights for one specific airline, say American Airlines. That's simple.
Right.
But then you could join that flight data with, say, weather data and ask, what were the exact weather conditions when flight A133 landed?
Connecting two different data sets.
Exactly. Or you could count how many flights took off from each airport and then order that list from busiest to quietest. Before SQL, trying to link, I don't know, sales data to inventory levels to figure out why returns spiked for product X in region Y, that was a manual nightmare.
Yeah, I can imagine.
Now it can be a single powerful query that potentially reveals crucial insights.
Okay, that makes sense. Relational databases, SQL, super powerful. But you mentioned the 80s. The digital world has changed a bit since then. Exploded, really.
Massively.
So think about something like Facebook or Instagram today. Millions of people posting, commenting, liking, all at the same time. Does that traditional relational model start to struggle there?
It absolutely can, yeah. That kind of massive simultaneous activity is exactly the sort of problem that led to the rise of NoSQL databases starting in the 2000s.
NoSQL, meaning not only SQL.
That's often how it's interpreted, yeah. Though originally it's more like NoSQL, as in not using SQL initially. Traditional RDBMS, the relational ones, typically scale vertically, meaning you make the one server they run on more powerful. More RAM, faster processor, bigger hard drive. But that gets very expensive very quickly, and there are limits.
Right, you can only beef up one machine so much.
Exactly. NoSQL databases are designed differently. They're built for horizontal scaling.
Okay, so instead of one super server.
You add more servers,
Yeah.
lots of them, potentially. You distribute the data and the workload across many machines. This makes them much better suited for these huge distributed systems, handling enormous amounts of rapidly changing data like you see on social media.
So NoSQL isn't just a buzzword. It's a different approach for flexibility, massive scale, better performance in certain situations.
Definitely. It's a fundamental shift for handling those modern big data challenges.
But does that flexibility come with trade-offs? Like, are relational databases maybe more reliable in some ways? I hear terms like ACID compliance with them.
That's a really important point. Yes, there are trade-offs. It's a core design choice. Traditional relational databases usually offer stronger guarantees about data consistency. That ACID thing you mentioned ensures transactions are processed reliably all or nothing, which is critical for things like financial systems.
Can't have half a bank transaction.
Precisely. NoSQL databases often prioritize other things in distributed environments, like being always available even if parts of the system are down, or handling network splits gracefully. Sometimes this means slightly relaxing those strict consistency guarantees. And NoSQL isn't just one thing. There are different types. Document databases like MongoDB are great for flexible data structures. Key value stores like Redis are super fast for simple lookups. Column family databases like Cassandra handle distributed data well. And graph databases like Neo4j are specifically designed for data with lots of complex relationships like social networks.
Wow, okay, so it really depends on the problem you're trying to solve.
Exactly. It raises that key question. What kind of data challenge are you facing? And how does that guide your choice of database technology?
And it's clear this whole area is still evolving, right? It's not standing still.
Not at all. You see newer trends like NewSQL. These try to combine the scalability benefits of NoSQL with those strong ACD guarantees from relational databases. Google Spanner is an example.
Interesting.
And then, of course, cloud databases are huge now. Services managed by Amazon, Google, Microsoft, where they handle all the infrastructure for you. That's becoming the default for many companies.
Takes away a lot of the headache.
It can, and you also hear about data lakes. These are massive storage places for just raw data, everything in its original format. Often used as the starting point for big data analytics. Think AWS S3 or Azure Data Lake.
So it's a really dynamic landscape. We've collected the data, we've stored it in one of these evolving database systems. Now what? How do we actually use it to make smart decisions?
Right. That's the crucial next step. And this is where an information management system, or IMS, comes into play.
The IMS.
The main goal of an IMS is pretty straightforward.
Yeah.
Get the right information accurately and on time to the right people so they can make good decisions. It bridges that gap between stored data and actual strategy.
So it's the whole system that makes the data useful. What are the key parts of an IMS?
Well, it typically starts with your data sources, where the data comes from. Then there's a critical process called ETL, extract, transform, load.
ETL, heard that one too.
Then usually a central data warehouse, an OLAP engine for analysis, and finally analytic reporting tools.
Okay, let's break that down. Data sources. How broad are we talking for a typical business?
Oh, potentially very broad. You've got internal stuff like finance data accounting, expenses, CRM, data customer interactions, operations, data supply chain, production lines, and then, like you said, more data.
Right.
Which could be anything. Website logs, sensor data from machines, social media feeds, again, external market research, pretty much anywhere the business generates or collects information.
Okay, that's a lot of different places, probably different formats too. So the ETL process, that's about bringing it all together.
Exactly. ETL is absolutely vital. First, extract. You pull the data out from all those different source systems.
Okay.
Then transform. This is where the real work happens.
Yeah.
You clean the data, fix errors, maybe aggregate it, standardize formats, basically get it ready and make sure it fits the structure where it's going next.
Yeah.
Quality control is huge here.
Right, get it all speaking the same language.
Perfectly put. And finally, load. You load that clean, transformed data into the data warehouse. ETL is really that essential bridge turning raw, often messy, data into organized, reliable information ready for analysis.
And the data warehouse itself, it's not just another database. It's more like a central library, maybe? Optimized for asking questions?
That's a great way to think about it. It's a large, centralized repository designed specifically for query and analysis, not for day-to-day transactions. It consolidates historical data from potentially many different operational systems. Your library analogy, or maybe like a company's historical archive, carefully cataloged.
Okay, so the data's in the warehouse, clean and organized. What's the OLR engine do?
OLS stands for Online Analytical Processing. These are the tools that let you perform complex queries and analyze the data from multiple dimensions.
Dimensions, like
analyzing sales, not just by total amount, but slicing and dicing it by time period, by geographic region, by product category, by customer segment, all at the same time and quickly. It lets you explore the data interactively.
Okay, so you can really drill down and see patterns.
Exactly. And the output of all this, that's where analytic reporting comes in. This generates the reports, the dashboards with charts and graphs, and also supports ad hoc reporting, letting users ask their own specific questions on the fly.
And beyond basic reports.
Then you get into advanced analytics. This uses more sophisticated techniques like data mining to find hidden patterns, or predictive modeling to forecast future outcomes. Really trying to understand the why and what might happen next.
And the whole point of this entire IMS structure, it's for the people making decisions.
Absolutely. It's all about empowering the users and decision-making. Business analysts, managers, executives. They use the insights from the IMS to move beyond just intuition or guesswork.
To make data-driven choices.
Precisely. It could mean improving operational efficiency, spotting risks earlier, identifying new market opportunities, enhancing customer experiences, all based on solid evidence from the data. It's about enabling smarter, faster, more confident decisions.
Okay, one more crucial piece, I think. Imagine someone hands you this huge data set, maybe in a spreadsheet, and the columns are just labeled VAR1, VAR2, COLE. You'd be completely lost.
Well, utterly lost, yeah. It's like getting a map without a legend.
Exactly. That's where metadata comes in, isn't it?
It is. Metadata is simply data about data. Information about your structured data.
Wrong.
Like, when was this data created? Who created it? What format is it in? What do the different fields or columns actually represent? It's the context you need to understand the data itself, like the label on the outside of a box telling you what's inside.
And a data dictionary is a specific kind of metadata.
Yes, a very important kind. Think of the data dictionary as the detailed guidebook or code book for a specific data set. It lists all the variables or columns, provides clear definitions for each one, specifies the data type, is it a number, text, date, maybe lists possible values, units of measurement, all the details you need.
The source material mentioned the empty cars data set as an example. That's a classic one in data analysis, right?
It is, yeah. It's built into the R programming language. It's basically a table with information about different car models from the 70s.
Okay.
It has columns like MPG, HP, SIL. Without a data dictionary, those are just abbreviations. But the data dictionary, which you can access easily in R by typing .mtcars, tells you MPG is miles per gallon, HP is gross horsepower, SIL is number of cylinders.
It's the instruction manual.
Exactly. That's what stops you from getting lost in just a sea of numbers and labels. It helps you make sense of it all, turning confusing data into something you can actually understand and use. Absolutely critical.
Okay, wow. We've covered a lot of ground from just understanding what raw data even is.
Structured, unstructured.
Right. Then through the whole history and evolution of databases, COD's relational model, SQL, then the rise of NoSQL for scale and all the modern cloud stuff and data lakes.
Yeah, the storage part.
And then connecting it all with the information management system, the ETL, the warehouse, OLP, the whole process to turn that stored data into actual insights.
And tying it all together with metadata and data dictionary so we know what we're looking at.
Exactly, making it usable. It's quite a journey from raw facts to informed decisions.
It really is. And it makes you think, maybe a question for you, the listener, to ponder. As data just keeps growing everywhere, in every part of our life, personalized ads, medical research, how we shop, everything.
Yeah.
How might a deeper grasp of how this data is organized, how it's structured and managed, how might that empower you to ask better questions, to make more informed decisions, not just in a business context, but just in how you navigate the world, in all the information coming at you daily?
That's a great thought. Really makes you consider how we interact with information differently when we understand the plumbing behind it. And, if this conversation has sparked your interest and you want to go even deeper, there are entire fields dedicated to this stuff.
Oh, absolutely.
The source material we used actually points towards university courses like database management systems, information security and privacy, data governance, information systems analysis, loads more to explore if you're keen.
There's always more to learn in this space. It changes so fast.
Definitely. Well, thank you for joining us on this deep dive into data organization. It's been really insightful.
My pleasure.
And thank you for listening. Until next time, keep asking those great questions.